Alright guys, today we're going to be talking about graphs of polynomial functions and the intermediate value theorem. So before we start, we're just going to go over some features of these graphs of polynomials. So first of all, the graphs are continuous, so that means that there are no discontinuities, no jump, no infinite, nothing like that. We can draw them without lifting up our pencil is another way to put that. They have at most n minus 1 terms, where n is the degree of the polynomial. So another way to put degree is to say the highest power. So whatever the highest power is, you take that and subtract 1, and that's the number of turns the graph can have. At most. It cannot have more than that, but it can have less than that. So the next thing is what we're going to call the end behavior. So this first one is the right end behavior. So right end behavior, what the graph is doing to the right. So that means as x is getting bigger. So if the leading coefficient, which is a, is positive or greater than 0, as the x's get bigger, the y's will also get bigger. So that means the graph is going to rise to the right without bound. So if you want to draw your little graph, just means that it's going up like that. Whatever the graph looks like to the right, it would be going up. And if the leading coefficient, or a, is less than 0, then as x is getting bigger, which means as you're going to the right, the y's will be getting smaller. So they'll be getting negative, so they'll be decreasing without bound. So this is what it would look like. Now what will happen to the left? So after you've looked at the leading coefficient, the next thing you're going to look at is the degree of the polynomial, which is still the highest power like we said before. And if n is even, then as we go to the left, this is another way to say as we go to the left, as the x's go to negative infinity, that way, the y has the same behavior as it did to the right. So if your power is an even power, if your graph rose to the right, it's also going to rise to the left. And if your graph fell to the right, because it had a negative leading coefficient, it also is going to fall to the left. If your highest power or your degree is odd, then as you go to the left, your graph is going to have opposite end behavior. So your y values will be opposite. So that's a pattern that we've already seen for odd, opposite, both start with O's. So what this is saying is if your leading coefficient was positive and your graph rose to your right, but the degree was odd, like cubed or to the 5th power, then it would have opposite end behavior to the left. And then also, if your graph had a negative leading coefficient, it would be falling to the right, but it would, if it had an odd power, it would be rising to the left. So example 1 is just practicing this before we get into the actual graphing of these, just to make sure that we're clear. So what I would encourage you to do is pause the video right now and try these on your own, and then check back in to see if you have the answers, or try it listening through it one time and then trying it on your own. So this first one right here, the number of turns it's going to have, n is equal to 3 because that's the highest power, so the number of turns is 3 minus 1, which equals 2. You don't have to show that math, you can do it in your head, but it's a good idea to see where it came from. Now what I like students to do for this part, just so that they get clear, when you're doing right end behavior, you're determining whether your leading coefficient is positive or negative, and your left end behavior is whether or not your highest power is even or odd. So it's a good idea just to write this on all the right and left end behaviors so that you don't get confused. So this one right here has a -2, so its leading coefficient is negative, which means it's going to be falling. So this says fall. Another way that we write fall mathematically with symbols is we say the y values approach negative infinity. So you need to be familiar with both notations. If it doesn't specifically say or doesn't prompt you in the problem, then you can write it either way. The next thing we're going to do is look at the highest power. So again, for this one right here, we're done with that leading coefficient. We're moving on to the highest power. Since it's 3, 3 is an odd number, so it's going to have opposite behavior. So to the left, this graph would rise. So the way that you can write that with mathematical notation is that y values are going to go up, or f of x is going to approach infinity. So on the next one, this one has n equals 4, so then that would mean it would have 3 terms. The leading coefficient is positive 1, so that means that it would be rising to the right. And because the highest power is even, it's going to match that end behavior. So just like we learned even graphs have the same, this is also consistent with today's lesson. Moving on, for this one, you're always going to make sure that these are in descending order by powers of x. So the highest power of x is first, and in this case it is, so we're good to go. So here n is equal to 8, but notice there's a different notation for the end behavior. First, let's acknowledge that it could have 7 turns. That's a lot of turns, but that's okay. So this is saying as x goes to infinity. So this is just a fancy way of saying as x is getting bigger, which means your right end behavior. So that's still our positive and negative. And so in this case, it's negative. So this graph is going to be falling, but notice our notation prompts us to not write fall. So it's saying the y's are going where? They're going to be going to negative infinity. So again, that just means fall, but you need to be familiar with both. This one right here is our left end behavior, so we're checking that highest power or the degree, and we're seeing if it's even or odd, and in this case 8 is an even number, so that means it's going to have the same end behavior as it did to the right, so this is going to be negative infinity, which means it's also going to fall. For this last one, just one more practice, n is equal to 7, which means that there are 6 turns, and that because the leading coefficient is negative, it's going to fall, so this would be negative infinity, and because the leading exponent is odd, it's going to have opposite end behavior, which means it's going to rise, so this is going to be infinity. So there's one set of characteristics that we need to be able to identify from equations of graphs. The next one that we want to be able to do, which we've actually done in 2.2, but we're just expanding it to more solutions, is to be able to find the zeros of the function. So finding the zeros is another way of saying find the x-intercepts. And if you recall, when we find our x-intercepts, it just means the function equals 0. So we're going to set this equal to 0. And solve that. Well, way back in a preliminary chapter, we learned that when something has 4 terms, the way that you can factor it is by factor by grouping if it is factorable. So we're going to go ahead and factor that way. So x squared, I can pull out an x squared from the first 2 terms, and then I can pull out a 4 from the next 2 terms, but be careful right there because when I pull out the negative 4, this term has to be switched to positive 2 so that if I were to reverse the process, I would still get the same thing that I started with. And now you can see both terms here have an x plus 2 in common. So I'm going to pull out that x plus 2, and my other factor that's remaining is x squared minus 4. This is a difference of squares, so I'm going to go ahead and factor that. X plus 2 times x plus 2 times x minus 2. So those are my factors. The zeros that these are going to make are going to be x equals negative 2 and x equals positive 2. If it says zeros, that's a good enough answer. If it asks you for x-intercepts, then you remember that's referencing a graph, so it needs to be in point notation. So you could have either of these right here. I would encourage you to try the next one on your own, again pausing the video just to try it out. It's always good for you to do that. It's good for your brain to mess with it a little bit before seeing the answer. So if you are planning on doing that, now would be a good time to hit pause. Otherwise, I'm just going to continue. So the first thing I'm going to do is, again, set this equal to 0. My personal preference is not to have a negative leading coefficient when I'm solving for 0. So a real quick way to get rid of that is to multiply both sides by -1. 0 times -1 is still 0. and this would be x to the fourth plus 4x, sorry, it should be minus 4x cubed, because I'm multiplying by that negative, plus 4x squared. So once we get here, what we're going to do is we're going to factor out the x squared, because that's the GCF. So whenever you're factoring, it's always easy to factor out that GCF first. So that's what I'm left with in this problem. Because I have three terms, I have a trinomial, which means I can factor it. We use the t-chart, but you can use magic square, you can use the diamond, you can use whatever your previous teacher has taught you. But this is what we end up right there. So what I want to point out here is that this still has a 0. You would set it equal to 0, and so if x is 0, it makes that equation true. So our two zeros in this case are 0 and 2. This one does repeat, and x minus 2 also repeats. You don't need to repeat them in your answer because they're still the same 0 of the function. And again, you can write it in point notation if it says x-intercept, and write it in just x equals if it says 0. Okay, so one last thing we need to cover before we move on to how to actually graph some of these is we need to talk about multiplicity. This is probably something new for you this year. They don't usually cover it in Algebra 2, but you may have seen it. So multiplicity is defined as the number of times a factor of the polynomial appears. So I just want to point out down here in the problems we just did, x plus 2, because it shows up twice when I'm factoring, has a multiplicity of 2. It means it has even multiplicity. X minus 2 is a factor, and it only shows up once, so it has odd multiplicity. When I move down to 2b, this has x squared is x times x, so x has a multiplicity of 2, which is even, and x minus 2 has two factors, which means that it has a multiplicity of 2, and it is also even. If I flip over to the back just to show you guys some more, x minus 2 has a multiplicity of 2, but x plus 1 and x plus 3 have a multiplicity of 1 because their factors only show up once. I think you're getting the idea with that, but if not, as we work through the problems, hopefully it'll become more clear. I do want to point out that if the multiplicity is odd, the graph is just going to cross through the x-axis, just right through it. If it's even, then it's going to bump the x-axis. So cross through would look something like this. So it comes through like that. You can't see that, so let me move paper over. It would look something like that. So here's the 0. It's just going to cross right on through. If the graph, the multiplicity was even at a certain 0, the graph would come up and then bump it and turn around. Also, the higher a multiplicity, the more the graph will flatten out. So let's hypothetically say this was like x minus 2 cubed, a graph of that, because it shifted off of the origin. If I had something like y equals x minus 2 to the 5th power, the difference would be that this graph would come up and it would get really flat right around that 0. It wouldn't come up as neatly. It would look almost like a horizontal line would go through it. So the higher the multiplicity, the more the graph flattens out. Even the even multiplicity will like flatten out more like that. Okay, so you'll notice that in some of the problems. So the higher the multiplicity, the more the graph will flatten out. So let's start with example 3, which asks us to sketch this graph right here. I'm going to focus this a little better just real quick. Okay, that's better. So what you're going to want to do, it's nice because this is in factored form. It's going to be really easy for us to find our zeros. But what we're going to do first is, because we need to know the leading coefficient and the highest power to get the end behavior and the number of turns, is we're just going to pretend like we would multiply this out and figure out what our first term would be. And our first term would be x cubed. And then we'd have some other stuff that other terms that we'd be adding. But when we're trying to graph, that's not as important as the zeros. So we're going to leave it like this, and we only need our first term. So if this is n equals 3, the max number of terms we learned is n minus 1. So that is going to be 2. The right end behavior, I just want to remind you, right end behavior is plus or minus, so since it's positive, it's going to rise. It's positive 1. A left end behavior is even and odd. Because this graph has an odd 3, that's our highest power, we are going to have opposite end behavior. So this graph is going to fall. To find our x-intercepts, I'm just going to show you the math. We should be pretty familiar with this now, but we set our function equal to 0 because we are not moving up or down. We're trying to figure out where the graph is crossing the x-axis, so the x's need to say, and we set each piece equal to 0. A lot of you can do this in your head, and that's fine. And we get x equals 3, negative 2, and 1. So because this one says x-intercepts, we're going to put it in point notation. I prefer to go least to greatest, but it's not a must for you. So there's my x-intercepts, and then we know with our y-intercept, that means that the x is 0, so I simply have to find f of 0, and I get that by plugging that into the equation. So f of 0 would be 0 plus, let's say 0 minus 3 times 0 plus 2 times 0 minus 1. 0 minus 3 is negative 3. 0 plus 2 is 2, and 0 minus 1 is negative 1. When you multiply all those together, you get 6. So our y-intercept is 0, 6. Okay, great. So now we have all these things, and we're going to be able to graph our function. So the first thing we're going to do is plot all of our x-intercepts. So all these guys, and then we'll plot our y-intercept. So negative 2, 0, 1, 0, and 3, 0. And then our y-intercept is 0, 6. We know that our graph is rising to the right, so you might want to do this in pencil, but rising to the right would look like this. You want to make sure that if you make a funky graph and it doesn't flow nicely, that you go back and erase it. But this is the furthest most to the left 0, so I'm going to make that one fall. So I didn't say that on this one. This one rises to the right, so you go to the furthest right 0 and make it rise. The next thing I have to do is connect these dots, and I know that this graph can have at most 2 turns. What you want to make sure you're careful of is the maximum, the relative maximum of this graph is going to be right in between these zeros right here. So normally you could calculate it, like right in the middle would be negative 0.5. You could plug it into your equation, but that gets a little tedious. So all we're going to ask you to do is make sure that you get that relative maximum right in between the 2 zeros. Now this one's only a distance of 2, so I'm going to make sure that my relative minimum goes like that. How high or low you go really depends on how close they are together. Because these 2 zeros are closer together, it's not going to dip as low as this one will rise high. It doesn't have to be perfect. We're just making a sketch here. If you wanted it to be perfect, you could plug in 2 into your equation and then figure out what that point is and plot it. But this graph is good enough for us. So we have our right and left end behavior, our zeros, our y-intercept, and our turns. So let's move on to the next one. The next one makes your life a little bit more difficult because it's not in factored form, but that's okay. We can factor it. So what we're going to do is we are going to come down here, and we can say right away that this has 2 turns. The right end behavior, the leading coefficient is positive 1, so it's going to rise. That's nice. We don't have to multiply that out just yet. And then it's an odd, so it's going to fall, just like the last one, but I wonder what's different. So we're plugging along and we're going to find our x-intercepts. So we get 0 equals x cubed minus 3x squared. And then what I'm going to do is I'm going to factor that using a GCF since one. So then I have that this equals x times x minus 3, which may look strange to you because we don't ever write that like that. But first off, my zeros or my x-intercepts are going to be 0 and 3. Hopefully you can see that. The one thing I need to point out to you though is right here, this has an even multiplicity. It shows up twice as a factor. So the difference is instead of our graph crossing through at that 0, it's going to do the bump thing. So watch how we do that. So first of all, this is going to be 0, 0, and 3, 0. I'm going to put a star right here, and you'll see this on the graph in a second. The last thing I'm going to do is find my y-intercept, and to find my y-intercept, I am going to plug in f of 0, which you can do mentally, but clearly it's just going to equal 0. By the way, shortcut, if 0, 0 is an x-intercept, then it's also a y-intercept. So just like we did before, we plot all the points that we just found. So there's my x and y-intercept in this case, and then right there is my other 0 of 3. This graph is going to be rising to the right, and then it's going to be falling to the left, and it has a maximum of 2 turns. So the way I'm going to get those 2 terms, like 3 has a multiplicity of 1, which means it's an odd multiplicity, which means it's just going to cross through. However, 0 has an even multiplicity. We see it show up twice as a factor, so instead of passing through this right here, it's just going to turn around. So it's going to do that. And now you can see where that second turn is going to be. So there's the first term, and then it's going to be right in the middle of those two, and that's how you can connect it. So this right here is showing up as a bump. This is considered crossing through. You can see. Another way that you can check this out, if you're like, is it crossing or is it going through? If something is crossing through the x-axis, it's going to have a sign change in the y values. So look at here, these y values are negative and these y values are positive. When I go to this one right here, as I get close to 0, all these y values are negative. But when I come to the other side of the 0, notice they're also negative. So there was no sign change. Okay, so I'm just going to go through example 5. Hopefully by this time you've gotten the hang of it. First thing we're going to do is we are going to pretend that we would multiply this whole thing out to find our very first term, which would be negative x to the 4th. Because it's to the 4th power, we're going to have 3 terms. The right-end behavior, again, plus, minus, because it's negative, it's going to fall. Left-end behavior is even and odd, because it's even, it's going to have the same end behavior, so fall. The x-intercepts, these are going to be real easy to find because you can just grab them from up there, so we're going to have 2, 0. But notice, even though this doesn't say squared, it's just multiplied out, there is going to be a bump there. And we have negative 1, 0, and negative 3, 0. So we're going to remind ourselves to watch out for that guy right there. The y-intercept, my suggestion to you is not to do the y-intercept in your head because you have this negative out in front. Actually do f of 0. And then you won't mess up. 0 minus 2 times 0 plus 1 times 0 minus 2 times 0 plus 3, which gives you negative 2 times 1 times negative 2 times 3, which means you have 3 negatives, so it's going to end up being negative. So this is 0, negative 12. So then we're going to plot our points on our graph. You can see 0, negative 12 isn't on there, but if that's the case, just label your point so that the grader knows that exactly where it's at. And then you have 2, 0, negative 1, 0, and negative 3, 0. And because the negative 1, 0 and the negative 3, 0 have odd multiplicity, meaning they show up only once, the graph is going to cross through on those, and because x minus 2, that factor has an even number of multiplicity because it has a multiplicity of 2 because it shows up twice, it's going to bump. So what we're going to do first is we're going to take care of our falls and our falls, so left and right end behavior. And then you know that the graph is going to cross through here, which means we're going to have a sign change. So first the y's are negative, and then when it crosses through after the 0, the y's are positive. And then on this one, we also know it's going to be crossing through because it has an odd multiplicity. So these y values started as positive and now they're negative. So you can see that turn right there. But we got to come down here and get that y-intercept. So this is going to come down here. And then there's our bump right there. So there's that graph right there. We're going to do one more together, but you really should be able to do these on your own by now. So for this one right here, it is in standard form, meaning that we're in term form. It's been multiplied out, so we need to reverse that and put it in factored form because that's the easiest way to find our zeros. So the way we're going to do that is we have 4 terms, so we know we need to factor by grouping. So we're going to pull out the x squared from the first 2 terms, and then we're going to pull out a negative 4 from the last 2 terms, and then you can see these 2 terms have an x plus 3 in common, leaving us with x squared minus 4, which is a difference of squares, so it can be written as x plus 2 times x minus 2. It's just easier to do that first, but you could very well start graphing first if you wanted to. So this is going to have 2 terms, the right end behavior, because the leading coefficient is positive, it's a 1, this is going to rise. And then even and odd, because the highest power or the degree is odd, it's going to have opposite behavior. Because I've already factored, I can get my x-intercepts right from there. So we have negative 3, 0, negative 2, 0, and 2, 0. And then my y-intercept is what I would get when I do f of 0, so I just plug in 0. You can plug it into this factored form or this form right here. This one's going to be the easier one because you're going to have 0 plus 3 times 0 minus 4 times 0, which all is 0 minus 12, so we get negative 12. So just like before, we are going to plot all these points, negative 3, negative 2, and 2. And then down here we have 0, negative 12 off the graph again. Everything has odd multiplicity, meaning each one of these is only to the first power, and since 1 is an odd number, we don't have to worry about any bumps. So this graph is going to rise, this one's going to fall, and because it's crossing through, that's going to do that because it's going to be negative y values first, and then positive y values, and then it's got to cross through here. So it went from positive y values to negative y values, creating a turn. Then we got to come down here and get our y-intercept and then go back up. So there's a pretty good graph there. Now example 7 is the kind of like pre-AP style questions, but it's pretty much a graph but in table form. So my first hint to you is if you ever have one of these, then you should be able to graph those points and come up with some sort of graph. So first of all, it tells you it's a polynomial function, which means it's going to look something like this. We know polynomial functions are continuous. We don't have to worry about piecewise or over this domain. We have that all right here. So read your directions carefully. The zeros in the table are the only zeros of the function. So those are our x-intercepts, and no zeros have a multiplicity greater than 2. Answer the questions that follow. Identify the left and right end behavior of the function. So what I want you to do on this one, if you're like, how the heck can I see that from a table? These numbers are getting bigger in the x direction this way. What are the y's doing as the x is getting bigger? So as x is going to infinity, the f of x is getting bigger or smaller? Well, it looks like as we're getting bigger and bigger, we're going to infinity, so this would rise. So let me say that again. These x's are getting larger, and so are these y values. And because this is a pretty large y value here, it's safe to assume that it's going to keep increasing, kind of like this graph up above. Now, for the left end behavior, we're saying as x gets smaller, as x goes to negative infinity, so we're going this way, and you can see as the x's are getting smaller, what are the y's doing? The y's are also getting smaller, and then again, here's a pretty large negative number, so it's safe to assume that it's not going to turn after that, and it's just going to keep going to negative infinity. So that end behavior on the left would be fall. Okay, moving on to up here, it says based on the end behavior, what must be true about the degree of the function, and give a reason for your answer. So what do we know about end behavior? We know that if it's odd end behavior, if it's opposite end behavior, it'll be an odd function, and if it's even, it'll have the same end behavior. And since we have the right rising and the left falling, we know that the degree is odd. And it says give a reason, since function has opposite end behavior. So that's how you answer that one. Moving on, identify the negative zero of the function. So be very careful here. The only type of pieces of a graph that actually are called zeros are the x-intercepts. So sometimes students get that mixed up with the y-intercept. The zero of the function means that y equals 0. It's an x-intercept. So it says identify the negative zero. So they're telling you that there is a negative 0 here. And if you look at this chart right here, there's only 2 zeros, this one and this one. Why are those the only 2 zeros? Because that's where y equals 0, which would mean it'd be the x-intercept. So identify the negative 0. The negative 0 is x equals negative 3. And what is the multiplicity of this 0? So this is sometimes hard for students to see from a table, but what I want you to do, and what I've kind of been leading you into so far, is look at these numbers just before and just after that 0. So more specifically, we're going to look at the y values here. So this y value, which is only half an increment to the left of negative 3, is negative. But then if I go half an increment to the right, it's positive. So what that tells us is that it crossed through the x-axis. So if you look up at this graph right here, this kind of is similar. At negative 3.5, it was below the x-axis, meaning the y value is negative. And at 2.5, now it jumps up above. So that tells us it had to cross through. So when it says right here, identify the negative 0, we said, okay, cool, that's x equals negative 3. What is the multiplicity of this 0? And we're going to say the multiplicity is 1. And you might be thinking, well, we know that the multiplicity is odd because it crosses through. How do we know that it's 1? The reason why we know it's 1 is because down here it says no zeros have a multiplicity greater than 2. So the only odd number that we have to choose from is 1 because of that. So multiplicity is 1. The y values just before and just after negative 3 are opposite signs. So graph crosses the x-axis. Let me put that up there so you can see it. The last question, D, says identify the positive zero of the function and what is the multiplicity of this zero, and give your reasoning. So you can look down at your chart and you can see that the positive zero is the other one. It's 1, 0. And it says what is the multiplicity of this zero, and give a reason for your answer. So what I want you guys to look at now is half an increment or just before that zero. This is positive 0.875. And then just slightly to the right, just a half an increment to the right of that zero, look at it's also positive. So what that tells us right there is that the graph did not cross through the x-axis. It just touched the x-axis at 1 and then bounced back and went back. So this one right here, we knew in example 5 there was a bump. So look at just before, like a half increment, those y values are negative, and then you come up to the 0 at 2, and it touches at 2, 0, and then when it turns back, those y values are negative again. So there was no positive y values right before or right after that 0, so that's what tells us it's a bump. So what we're going to put right here is that the positive 0 is x equals 1. And we know from the previous example, or the previous question, that we can't have a multiplicity greater than 2, but since there's a bump, we know that it's even, so that one has to have a multiplicity of 2. And then our reasoning is that the y values just before and just after one don't change signs, or they have the same signs. So it bumps. So it bumps the x-axis. Okay, so that's the last little part of graphing. Although one last thing we're going to go over is the intermediate value theorem, or the IVT. When you have this on your test, you need to follow the way that we do this example exactly to get full credit. So this is a theorem that's used in calculus, and the way we set you up in pre-calculus is the same way you would approach this problem in calculus to get full credit on the test. So it's very important that you memorize the pieces to this theorem right here. It's called the IVT, or intermediate value theorem. Intermediate meaning in the middle. So it says if f is continuous, so that's kind of a condition we have to address before we can approach any problem using this theorem. If f is continuous on some interval and n is some number between two y values, then there is at least one value of x between a and b, such that when you plug in that x value, you're going to get an n. That sounds super confusing, but let me draw you a diagram first to see if that's a little bit more helpful. And then we'll show you how we use it in this class and in calculus specifically. So this one is saying if you have some x value a and some x value b, and here is f of a, because when you plug in a, your y value is f of a. And then up here is f of b, meaning when you plug in b, there's b's y value. All this theorem is saying is to go from a low a value, or a low f of a value, to a higher f of a value, there had to be some number n where when you plugged in c, so that's what this is saying, f of c is in between these. So the way that we like to use this is we like to use it more along these lines. It makes it a little bit easier to understand. So basically this, if you had an x value, like let's call it 1, and its corresponding y value is -1 down here. And then you had another x value, let's call it 2, and its y value was 1, so this is the point 2, 1, and this is the point 1, -1. Then at some point, somewhere between -1 and 1, it has an intermediate value, and in this case it had to be 0 because you went from a negative y value to a positive y value. So somewhere in between 1 and 2, this graph had to cross through the x-axis, or had to have a y value of 0. So it was the intermediate value. So the intermediate value in this case is 0. But with all positive numbers, I mean, it kind of makes sense. Like if this is 1 and this is 3 and the graph is continuous, then at some point it had to go through a y value of 2. But the way that we most often use it in calculus or in pre-calculus is by showing that when you go from a negative y value to a positive y value, that's proof that at some point you cross the x-axis, because how else do you get from negatives to positives without going through 0? So, with all that said, pay special attention to how we do this intermediate value theorem. So I'm going to put a tricky on it because this should you memorize. This is what you do. All these steps for this right here. So it says, show that the polynomial function f of x equals 3x cubed minus 10x plus 9 has a real 0 between -3 and -2. Notice nowhere in here does it say use the IVT to show this, but that's what you do, is you use the intermediate value theorem to show this. So it's not asking you what the real 0 is. All it's asking you is to show that it's between -3 and -2. So the first thing you're going to do, you kind of make these little bullet points right here, is you say let f of x equals 3x cubed minus 10x plus 9. So you're saying we're going to start with this function, and we're going to say since f of x is a polynomial, it's continuous on the interval from -infinity to infinity, and therefore continuous over the interval between -3 and -2. And you might be wondering, what the heck, why did we even have to write that? So back up here at the top, whenever you're using a theorem, you need to meet all the conditions of the theorem. So the first condition is that f is continuous on AB, and AB represent the two values right here. So since we're trying to prove that there's an intermediate value between -3 and 2, we have to show that our function is continuous from -3 to -2. Well, since this is a polynomial, it's continuous everywhere, so therefore it's guaranteed to be continuous on that interval as well. Okay, so that little 3 triangle symbol means therefore in math, just in case you didn't know that. So that's the first piece, is just meeting the conditions of your definition. The second piece is we're going to show that there is a sign change in the y values between these two here. So the way you do that is you plug in -3, and you end up with -42, which is less than 0, so you want to get that part in there. And then you also want to show that f of -2 that equals 5, which is greater than 0. So right there, look at the y value that goes with -3 is like -42, and the y value that goes with -2 is +5. So what we're saying is, since f of -3, which is the -42, is less than 0, but the f of -2 is greater than 0, intermediate value, it's in the middle, there is a number c in the interval from -3 to, now you might be wondering, why the heck did we switch from brackets to parentheses here? Well, keep in mind this is called the intermediate value theorem, and we're also using the definition up above. The number can't equal -3 or 2 and be in the middle, like the intermediate number. So that's why we're using the definition up here, the second part of it, at least one value c in the interval a, b. So there is a number c in -3, 2, such that f of c equals 0. Your very last step is to say, therefore, by the IVT, f of x has a real 0 between -3 and -2. So again, the problem on your test, you have to spell this out. So if this doesn't make sense to you, it's one of those situations where you just have to memorize it. So the first condition right here, based upon the definition, is that f is continuous on the closed interval. So we say we have this polynomial, and since it's a polynomial, it's continuous everywhere, and therefore we can conclude if it's continuous everywhere, it's even continuous between -3 and -2. Then what we're going to do is take f of -3 and get our y value, which is -42, and show that that's negative by writing less than 0, or you can write that it's negative. And then we do f of -2, and notice we get +5, which is greater than 0, or you can just write that it's positive. And since right here 0 is in between those, it's the intermediate number between the -42 and the 5, there has to be a number c in that interval such that f of c equals 0. And that's just, again, going like with this. Then there is at least one value c in a, b. Our value of c, our f of c will give us 0. We don't know what c is. That's why we're writing this. We don't know what value of x is giving us a 0, but we know that it's going through 0 without knowing it for certain. And then the last piece of this is to say, therefore, by the IVT, f of x has a real 0 between -3 and -2. And the reason why you need that statement is because you're using that theorem. So because you met all the conditions to use the theorem, you're going to tell your grader that you used it and used it properly, and therefore there has to be a real 0 between those two. Alrighty, that's it for today.